Thank you. So I'm Kris Luyten. I'm from Hasselt University from Belgium, and I'm here today to present our paper, Hidden in Plain Sight. It's about our exploration of a visual language for near-eye autofocus displays in our peripheral view. Allow me to start with some motivating examples why we're doing this work. Maybe you know this situation. In our lab we have a couple of these Google Glass devices, and we noticed that sometimes during a conversation, people who were wearing these glasses get a notification through the Google Glass device. And what happens then is that they check the notification and they have to shift their focus away and they kind of stare in the void to check that notification. Something what I like to call the dead stare. You're in a conversation with somebody and suddenly they stare away in the void and the focus is completely shifted from the conversation, which is often awkward that they shift their focus away to check their email on the Google Glass device. It's not something very nice to do. Another example is that if you're in a mobile situation, we're checking mobile information on a mobile device, that our focus is also shifted to that mobile screen and we're unaware of our environments. Although sometimes we only need to glance on our mobile device, for example, to access some routing information, we can still end up in a dangerous situation because our attention is drawn away from our surroundings. Finally, something what also inspired us was a current evolution in peripheral displays in cars. Maybe you know these kind of heads-up displays that you can find in some cars, which is a glass pane mounted on top of the dashboard, which allows you to access, for example, the speed you're driving. Now it allows you to have a minimal focus shift while you're driving to check your driving speed. Instead of having to switch your focus from the traffic to the dashboard, you can now just glance down and you're still aware of the traffic conditions. So there's a lot of benefits having these kind of peripheral displays, certainly if you don't have to check your focus. So that was our main question. To what extent can we convey information through the peripheral view using a depiction that fits on the temple of glasses, using a very small screen, and that doesn't require a shift of focus. That doesn't even allow you to focus on the display. Can we come up with such a visual language to accomplish this? Now, we're not the first ones who are trying to do something in the peripheral view. I think a notable example of an experiment which is similar was IQ by Costanza at Mobile HI 2006, where they mounted a series of LEDs on the temple of glasses. And they checked whether they could provide subtle clues to the user of these glasses. They did some experiments, for example, navigation experiments, telling the user through these LEDs where they should turn left or right. And they found that despite this low resolution display, they can effectively inform people about things to do without them having them shift their focus. From the same group is Peripheral display, where they try to combine foveal and peripheral visualizations in one. Interestingly, they noticed that if you want to inform people about something in the peripheral view, you have to use contrast and motion or animation. And that works fairly well to inform people in the peripheral view without them requiring them to shift the focus. Now, this has been investigated before. For example, at CHI 2000, Maglio had a paper on the trade-offs in displaying peripheral information. And they noticed that animation can be quite disruptive. If you animate something in the peripheral view, it draws your attention away and your focus will shift to the animation. So you have to be very careful how you design the animation and make it discrete. Specifically, continuous animations can be quite disturbing, can be quite interrupting. 1 year after that, at Interact 2001, McCrickard had a paper on similar things, and they found if you designed animation in a good way, that it has a minimal negative impact. So you can provide animation in the peripheral view without people shifting their focus, informing them about subtle things. So if you have smooth animations, it becomes less distracting and you get informed in your peripheral view without having to shift the focus on the animation. Now, our setup in our study is a frame which holds two displays. And we have quite a big display size to allow us to explore the optimal visible area. So during our study, we used this setup. We also brought it over here, so if somebody wants to try it afterwards, just talk to us. We can show you how it works and how we did the experiment. We use an acrylic glass structure in which two RoboPeak displays are mounted, which is fitted out with small cushions and a strap to increase comfort. Both displays can be controlled using the USB connection and using a single device. So they can be steered using a Raspberry Pi or a laptop, for example. We developed a custom altering tool for our studies, which can be used to program both displays, to steer the visualizations, to select what shapes to show, what animations to provide. So in our study, we had within subjects experimental design, and across all experiments we had 18 persons participating, of which 7 female and 11 male. Roughly there are 2 different things we try to explore. First, planar variables, which is actually exploring the visible area in your peripheral view. What kind of area can we use to show people things? Secondly, we explored the so-called retinal variables, which is the typical visual language. So we asked people to identify shapes in the peripheral view without prior knowledge of these shapes and with prior knowledge of these shapes and compared this. We also looked into how animations work, where animations help you to identify the shape that's being animated, and where you can recognize the path of an animation. And finally, we also explored the degree of user control. If you can control a visualization in your peripheral view, how precise can you control this visualization? So that's what we did. So first we explored the planar variables, which is actually the usable screen space. In the first step, we showed objects in various sizes and colors. None of our participants were color blind, by the way. Now, we noticed that red, green, blue, yellow, purple, and orange are easy to identify by all participants, and we also asked them to tell us their preferred colors, which we would use later on in the remainder of the experiments. To explore the usable screen space, we divided the display in a 10 by 10 pixel grid, and for every intersection on the grid, we showed them a color dot in the preferred color and asked where they could still see the dot. If they could still see the dot, we moved the dot 10 pixels further along on the vertical axis, and after that we moved the pixel along on the horizontal axis. In the end, we ended up with the top extremes and the bottom extremes of the visible area for each individual participant. Then we combined all this data and we found a minimal visible area for all participants. And we used this area to display our glyphs to the users. And of course, the difficulty is that if you bring a graphical depiction very close to the side of the eye, it automatically becomes harder to focus on it and recognize it. So if you bring it very close to the eye, you get this kind of blurring effect. Some people see this, but a lot of people see this. If you want to try it after on and put on a device, you will notice that if you have this graphical depiction very close to the eye, you get this very blurred image of things, which becomes very hard to recognize. In our study setup, we wanted to simulate the worst case scenario. So we had an eye tracker in front of the participant, and we made sure that the focus was straight ahead of the participant, so they were not glancing or trying to glance on the displays. They had to look right in front, and we could check where they were doing that. In our first step, we showed them a set of static glyphs. They didn't have any prior knowledge on the glyphs, and we asked them to describe every glyph we showed to them. The recognition rates for static graphical elements were not that good. In green, you see when they described the correct glyph. In yellow is if they described something which was like the glyph but not precisely the glyph, and in red if they could not recognize it all. So most of people have an idea what they've been shown, but they cannot explain very precisely what they've shown. Here's an example of 2 arrows. You can see that the arrow pointing to the left has a lower recognition rate than the arrow pointing to the bottom. Now, if we then provided them with a visual reference so they could point out what they saw on a paper sheet, the recognition rates were much, much better. So if you have a limited set of static glyphs and people are informed about what the possible glyphs are, the recognition rates becomes much better. If you compare for the 2 arrows the recognition rate when they know what they might be shown with the recognition rates without the visual reference, you could immediately see there's a big improvement if they have some prior knowledge on what they see. So the next step was to show them animated glyphs, and we wanted to answer 3 different questions. Can the recognition of the shape be improved by means of animation? Can they recognize the path of the animation? And can they also control the animation? If we provide means to interact with it, can they have precise control over the animation? We use several types of animation during a study. So we have glyphs that grow and shrink, change size. We have glyphs that move in a linear movement. Here's an arrow moving to the right. We have glyphs that change color. Here's an animation that changes from green to red, a bar that slowly fills up in red color. We have things that circle around, animated full circle. And we have also objects that move with respect to each other. Here the circle moves on top of a square. Now, as you can see in this graph, the recognition rates for what shape are not much better. Sometimes they're even worse. So it's very hard for people to recognize the shape of something what's being animated. In contrast, the recognition rates for the animation path, if we ask them what kind of path, does something move in a certain direction, or does something grow and shrink, or does something change color, they can describe this fairly precisely. In the last step, we tried to see how precise they could interact with the visualization. Using the left and right arrow keys, they could control the change of color in a bar, and we asked them to fill up a bar up to 50%, up to 75%, and up to 100% with different color. In a fourth task, they were asked to move a circle across the screen until it was exactly on top of a square of another color. And most tasks could be performed with a fairly precise, within a fairly precise way. Overall, it seems that if participants can control the visualization themselves, that it's easier to understand what's happening. We did the same thing for rotation, which didn't work that well. You can see that the offset rotation is a bit much higher. If they reach 0 degrees, they reach the goal exactly, but most people under or overshoot a bit in the number of degrees. So rotation is much harder than movement. So for these tests, in summary, we noticed that you can achieve very little if you provide static glyphs on a screen without the user having prior knowledge about what he can be shown. But if you give a user a limited set of possible shapes beforehand, the recognition rate already improves a lot, and you can do much more. If you add motion, that's a powerful tool for communication in the peripheral view. And finally, precise interactive control is also possible. Now, with these findings, we're now trying to do the next step in our research, and we're trying to investigate how we can combine the peripheral information while doing a primary task. Here's one example of somebody reading text out loud. Real-time feedback on the reading performance is given using the peripheral displays, using a system we presented last year at CHI. So the system informs the user whether it should change volume, should change pace, or be more bodily expressive. You can notice that the person here is reading the text continuously while being informed and trying to change the style. We're also looking into whether we can accomplish fine-grained navigation with it. So this is a navigation task where somebody has to move across a set of points, designated points, and he's guided through the peripheral displays, turning around and moving through the room. As you can see here, you can move fairly precisely within a room using these displays. Now we're trying to combine this with a primary task. Here the user has to push a highlighted rectangle on a mobile device while moving through the room. And we are comparing now how well the primary task is done while the user is moving through the room. We don't have all the data yet. This is something we're still doing. We're currently investigating this and collecting data and seeing how much of an interruption the peripheral displays lead to. So that concludes my talk. Thank you for your attention. If there are any questions, we'll be happy to answer them. Thanks.
So those are questions. Please back over to the microphone.
Hello, Miguel Nacenta, University of St. Andrews. Great work. I really
Thanks.
like this. The focus problem, do you think if the image was sharp, the results would have been very different in terms of recognition of shapes, etc.? Still controlling that people didn't look at it, or because I believe that technically this is not very difficult to achieve these days.
But the image displayed was sharp on the side. But when you see it, when you look at it, it becomes very blurred because there's no good transformation to make something which is very close to the eye, on the side of the eye, sharp. So you always see a blurred image over there.
Well, because of the peripheral resolution of your retina, you're referring to that? Okay.
If you can test yourself, so if you move your hand backwards and you see your hand here, it is a blurred object. You cannot focus on it.
I'm just wondering, so is that just the only factor? Because I mean, where you're focusing and where your depth of field is also will affect that. So I wonder whether the blur comes also a little bit through the fact that you're looking elsewhere and focusing something that is maybe 10 meters away.
Well, in our case, we're pretty sure that you cannot avoid the blur because the screens are located in such a place that it's impossible to focus your eye on it. So if you have your screen here on the side of the temple of your glasses, you cannot turn your eye and you can never focus on that bit of the screen. But there's still a visual area which you can observe through the peripheral view. So you can never focus on it because you cannot shift your focus in that direction.
Okay, thank you.
Hi there, I'm Christopher Dye from Illumina. I'm just wondering, did you notice any difference in people who were nearsighted versus farsighted? Any sort of differences just on their visual capabilities?
No, we didn't notice any difference. We had both of people in the group. None were had really bad sight, but some were nearsighted, some were farsighted, and we didn't really notice any difference if it's that close to the eye. I think it also has to do with the focus. Since you cannot focus on it, it works differently here. It's just a peripheral view that gives you some information, but it's blurred anyway. So we didn't really notice any difference. Also not in the results in the end.
Great. Thank you.
Okay.
So actually I have a two-part question if you have time to answer it. One, how did you choose the glyphs that you chose in your study? And two, in what scenario would you imagine people actually wanting to move something on the side, and why you included that in your study?
First question is a difficult one. We also thought a lot about this, how to choose the set of glyphs we used. So what we did is we did a couple of iterations with different authors and tried to come up with a set of glyphs that had both basic shapes and composed shapes with different angles and different colors. Since previous literature already showed that you have to keep things very simple in the glyphs, we end up with a set of limited glyphs where you have like rectangles, triangles, and some very basic shapes. And we added 2 or 3 complex shapes, so there's a small face in there that's a bit more complex shape, but that was mainly to see whether people would be able to see this, but that didn't work. On the second question, what was that again?
In what scenario would you imagine people
Okay.
wanting to move something in the periphery?
That's a good question. One of our ideas was that if you, for example, are doing backwards parking and you want to look back, you might get this range information through the peripheral view. So while you're driving back, you will see the shifting in your peripheral view. And we thought it might be a good idea. The interactions then driving back, and you should stop when, in the peripheral view, the circle is close to the rectangle, for example. And in that case, you might want to move things. Yeah.